I'm going to be talking about work from the past couple of years, largely with Steve Schenker, but also with Dan Roberts, with Lenny Susskind, and with Juan Maldacena. I'd also like to point out some nice related work which has been done by Alexei Kitaev, Stefan Leichenauer, and Joe Polchinski. Most of what I'll have to say has to do with probing chaos in quantum systems using certain four-point functions. And so I'd like to start by illustrating the type of chaos I'm going to be talking about and why these four-point functions are relevant. So I'm going to walk through a thought experiment that illustrates this. Let's imagine that we have a pure state that approximates local equilibrium at some temperature, inverse temperature beta, in a nice interacting quantum system. So the line at the bottom there, the horizontal line, indicates thermal equilibrium at time t equals 0. The higher line indicates thermal equilibrium at time t. Okay, so let's act on this state with a thermal scale local operator v that acts on one of the many degrees of freedom in the system. This gives us a slightly non-equilibrium state with a little blip at the location of the v operator. If we evolve forwards in time, if the system thermalizes, then this blip disappears into the thermal soup, and we get thermal equilibrium at a later time t. But secretly, the state at this later time t remembers the perturbation. One way to expose that would be just to evolve it back to time 0. Now this blip will reassemble itself. The reassembly is kind of a delicate process, though, and if we act with a second operator at time t before evolving back to time 0, then we might wonder whether this perturbation will succeed in rematerializing. Okay, and I claim that if the system is chaotic and the time t is long enough, that it will not. The v blip will not appear. So that what we'll have is the state w of t times v acting on beta will have a small departure from thermal equilibrium at the location of the w operator, but at the earlier location of the v operator, we'll just have local equilibrium. Okay, so that's the story for this state on the left, w times v acting on beta. There's a similar story for the state with the operators in the reverse order. There we have a disturbance at the location of the v operator, but not at the location of the later w operator. So we'd like to quantify this somehow, and a simple thing to do is to note that based on what I've said, these states should be distinguishable, so their overlap should be small. And one definition of the butterfly effect for these types of systems would be that this type of overlap, which is an out-of-time order four-point function, should be small at large t independently of the choice of w and v operators. Okay, so the first goal in this talk will be to show how to calculate these overlaps, these out-of-time order four-point functions using holography, and see what we get. Actually, to make the pictures a little bit more symmetric, I'm going to move the 0 of time so that we have w acting at time t over 2 and v acting at time minus t over 2. Okay, so let's start by warming up by showing how to construct. Yeah, I should mention the strategy here. The strategy for computing these things in holography will be to represent these two states in the bulk and then take their inner product in the bulk. So to warm up, let's understand how to represent this state where we just act with one operator at time 0 on an equilibrium thermal state. Well, a thermal state at sufficiently high temperature is described in ADS-CFT by a large ADS black hole. Here's the Penrose diagram for a large ADS black hole. I've drawn here a two-sided black hole. For the experts, let me mention that it doesn't matter. The same types of analysis apply to one-sided black holes. The picture is a little bit simpler here. Okay, and we acted with an operator w at time 0. And what this does, this is a thermal scale operator that adds an amount of energy of order the temperature to the system. It effectively adds an extra Hawking quantum. And if we were to follow the trajectory of that extra particle, it comes out of the past horizon here. It approaches the boundary at time 0, and then it falls through the future horizon here. I've drawn something like a classical trajectory for this particle. The squiggly lines are there to remind you that really we should think about a wave function for the particle, which would be computed by the bulk to boundary propagator from the point of insertion of the W operator. Okay, good. So now we'd like to move this thing up to time t over 2. One way to do that is to apply a time translation to the previous picture. There's a very important fact, which is that time translations in the black hole background act as Lorentz boosts of the near horizon region with a rapidity that's given by 2 pi divided by beta, that's 2 pi times the temperature, multiplied by the difference in time. This is a fact that might be familiar from Rindler space. It is a very important fact for this talk. So if we apply this transformation, then what happens is the wave packet of this quantum is Lorentz contracted onto the horizon here, onto this horizon, and its energy is boosted. So the p plus component of its energy becomes large by this exponential boost factor. So if the energy was of order 1 over beta before, then the p plus is now of order 1 over beta times exponential of pi t over beta. Okay, we can represent this quantum on different slices in the bulk. It'll be convenient to represent it on a time slice that touches the boundary at an early time minus t over 2. That makes it easy to add the second operator. So now we act with v at minus t over 2 on this state. That just adds a second quantum here, which is following a similar kind of trajectory, but boosted in the opposite direction. So W has large p plus, and the v quantum has large q minus. So altogether, this state consists of 2 particles in the bulk, which are highly boosted with respect to each other, traveling along these 2 horizons. And they're destined for some kind of a collision here near the bifurcation surface. In other words, what we have is something like an in-state for a scattering problem. Scattering problem with large center of mass energy happening near the center of this diagram. Okay, we could have done the same construction for these operators in the opposite order. What one finds in that case is something like an out state, but with the same type of kinematics. This means that the overlap of the 2 states, which is the thing that we're after, is basically a scattering amplitude, an overlap of an in-state with an out state. And the scattering amplitude will be weighted by wave functions appropriate for the insertions of the W and V operators. This scattering amplitude is characterized by 2 very important quantities. One of them would be the center of mass energy, or its square, the Mandelstam invariant S. So based on the previous 2 slides, we know that the typical value of the Mandelstam invariant S in this collision will be the product of the typical values of these momenta, p plus and q minus, for the 2 quanta, which will be of order 1 over beta squared times a big exponential e to the 2 pi over beta times t. The other important parameter would be the impact parameter, or the separation of the W and V quanta in the direction coming out of the screen, the direction along the horizon. This is actually, the dependence on the impact parameter is very interesting, but we'll have enough to talk about here just focusing on the dependence on S. So I'm going to suppress all dependence on the impact parameter for the rest of the talk. Okay, so we can write now an equation for this overlap, this out-of-time order 4-point function, as an integral over the momenta, where we have these wave function factors here. These would be bulk to boundary propagators from the points of insertion, the operators, multiplied by the scattering amplitude for this process, which we can parameterize as a complex number e to the I delta of S. So delta is in general complex. It's sometimes referred to as the iconal phase. So if you have a theory of the bulk, and you know how to calculate this scattering amplitude, you know how to calculate delta of S, you plug it into this formula here, do the integrals, and that's your answer for this overlap. So it's interesting. Well, the example we'll consider first is the case where the bulk theory is just gravity, and then the scattering amplitude is a scattering amplitude for a gravitational exchange, iconalized gravitational exchange. Yeah, so somewhat surprisingly, it turns out that the relevant regime of the gravitational scattering for this correlation function is the elastic iconal regime, where this iconal phase delta can be calculated by a variety of methods. The one I like best is by thinking about one of the quanta as sourcing a highly boosted gravitational shock wave and then studying the propagation of the other quantum on that background. This was done by a Tuft for flat space scattering. And it can be done in the ADS background just by using ADS appropriate shock waves. Okay, so however you do it, the answer you get is the phase is real, and it's proportional to g Newton times the Mandelstam S. So in particular, g Newton is a small parameter, so this is small, it's suppressed by g Newton, but it's growing with the center of mass energy. This is a familiar fact that gravitational interactions grow in strength with energy. But since g Newton is a small parameter, then it's very sensible to think first about expanding this exponential in powers of g Newton. Let's look at the first two terms. First, we have a term where we replace this amplitude by 1, and then we can do the integrals. We just get two decoupled integrals. We get the norm of the product of the norms of these two states, or what's the same thing, the product of these disconnected two-point functions, the product of the v squared and the w squared two-point functions. Okay, so that's this 1 here. That would be if there was no scattering. The first non-trivial term is when we expand down I g Newton times s from the exponential. And I've told you on the previous slide or so that the typical value of s in the scattering problem is of order e to the 2 pi over beta times time. So we can put that in here, and we get this behavior. In particular, the correction to the disconnected two-point function answer is formally small. It's suppressed by g Newton, but it's exponentially increasing as a function of time. This type of exponential growth is a generic feature of chaotic systems. It's a ubiquitous feature of chaotic dynamics. And it smells like a Leaponov exponent. So we'll follow Kitaev in referring to this 2 pi over beta here, the coefficient in the exponential, as the Leaponov exponent. So what this calculation was to show was that in gravity, this Leaponov exponent is 2 pi over beta. Okay, if we go to large times, then this exponentially growing term will be large enough to overcome the g Newton suppression, and this expansion won't be very good. Instead, what we have to do is really do the integral. And at very large times, this phase will be large and oscillating rapidly as a function of momenta. It will tend to suppress the integral. The integrand will be. So in this talk, what we'll be mainly interested in is the behavior of this function in this region here, where it's almost equal to this disconnected answer, but there's a correction, and the correction was growing exponentially. So it's worthwhile commenting on this a little bit more. I'll go back to this slide to mention that the source of this exponential growth here was nothing but the fact that the gravity scattering is growing with energy. And the fact that specifically we got this behavior e to the 2 pi over beta times time was a result of two facts. One fact was that the typical value of the Mandelstam invariant S was exponential e to the 2 pi over beta times time. And the second fact was that this phase was linear in S. Okay, so we can imagine changing the bulk theory a little bit to try to understand how robust this conclusion is. There are a couple of stupid things we could do. One might be to change the W and V operators that we consider, and that won't make any difference to this exponential here. That might change the prefactor. But because everything couples to gravity, this term will be present for any choice of W and V operators. Another thing we could do is we could imagine adding higher derivative interactions to the bulk theory. Those won't change this either, because really what determines this power of S here is the spin of the graviton. And the spin of the graviton is 2, even in the higher derivative theories of gravity. There is something we can do, though, that will change this, which is to consider stringy corrections. We're used to the idea that Reggie behavior of strings makes amplitudes in string theory grow a little bit less rapidly with energy than in gravity. And one can analyze the first correction to the Regge-intercept for the scattering problem near the bifurcation surface of the black hole. And what one finds is that this phase, instead of being linear in S, it's like S to the 1 minus a small quantity, where this number is positive and calculable, it depends on the geometry of the black hole, times alpha prime over L80S squared. So this is a slightly slower growth with energy, and it translates to a slightly smaller Leaponov exponent. So it would be 2 pi over beta times 1 minus a little bit. Okay. So there's some evidence in this paper that was mentioned in the last talk by Kamanho, Edelstein, Maldacena, and Zhuboyedov that suggests that this linear behavior from gravity is actually the fastest growth that's allowed by unitarity, analyticity, and causality. So this motivates an interesting conjecture that maybe there's a universal bound on lambda L. It can never be bigger than 2 pi over beta. This is sort of morally similar to the viscosity to entropy conjecture of Kovtun, Son, and Starinets. The advantage, though, of this conjecture is that it's possible to provide a simple and mathematically strong argument in favor of the bound. And that's what Steve Schenker and Juan Maldacena and I did in a paper that came out a few months ago. So I'm going to describe that a little bit in the last few minutes of the talk. Our argument revolves around this function f of t, which is similar to the out-of-time order 4-point function we've been considering so far in the talk. It's a little bit different. Rather than being an expectation value in a pure thermal state or a thermal ensemble, it's like an expectation value where we've split up the thermal density matrix into 4 factors and put them between the operators. A nice way to understand this correlation function is to think about the path integral contour that would compute it. So this is a diagram of that. The circle is the Euclidean circle, the thermal Euclidean circle. And these folds here are the Lorentzian evolution to produce the operators W of t. Each of the operators is separated by 1/4 of the thermal circle. That's these factors of y. And the contour ordering is VW, VW. Okay, so that gives us this. In our paper, we were careful to provide a very general argument that should be valid for pretty much any system, any quantum system with a large number of degrees of freedom. But to make the presentation a little simpler, I'm going to study a special case in this talk, a special case where we consider a theory that satisfies large N factorization, and also where we assume that the thermal 2-point function of the V and W operators is 0. This isn't necessary, but it makes the presentation a lot simpler. What these two assumptions buy us is that f of t is given by fd, this disconnected answer, plus something that's formally 1 over n squared. Okay, I'll use this fact in a minute. So you can do a holographic calculation of this f of t in the same way that we did a holographic calculation of the overlap we were studying before. And what one finds is f of t is equal to fd minus 1 over n squared times this familiar growing exponential plus higher orders in 1 over n squared, higher orders in g Newton. Good. So what we would like to do is we would like to bound this exponential growth. So one way to formulate that would be to bound the difference between fd and f of t. So if we could show that the difference between fd and f of t was not growing too rapidly, then we would have some kind of bound on this Leaponov behavior. The strategy for doing that is as follows. First, we notice that the function f of t can be extended to an analytic function and a half strip of the complex time plane. Actually, a whole strip, but we'll only be interested in the half strip with positive real part of time. The way I like to think about this function at complex values of time is as follows. The lengths of these folds here are the real part of time, and the relative angle on the circle of the v operators and the w operators is the imaginary part of time. Okay, so here's the strategy. If we can show that the norm of f is less than or equal to fd, this disconnected answer, plus some small epsilon, everywhere on the 3 boundaries of this strip, then some results from complex analysis will imply the following bound on the derivative of fd minus f of t. This was the thing we wanted to bound. And I'll show in a second how this implies exactly this bound on the Leaponov exponent. Okay, so what are these things here? The Fragment-Lindelof principle is like the maximum modulus principle for strips. So it says that if we've bounded f on the boundaries of this strip, we've bounded it on the interior. And the Schwarz-Pick theorem bounds the derivatives of functions that map the unit disk into the unit disk, or in this case, a half strip into the unit disk. This result is actually kind of intuitive. It says if we have, suppose you had a function that was bounded by 1 in a strip, and it was very close to 1, so that right-hand side is small, then it can't decrease too rapidly along the real axis. Because if it was decreasing rapidly along the real axis, it would be increasing a little bit in the imaginary direction, and it would violate the bound of 1. Okay, so how do we do this? Our task is to bound f on these 3 boundaries. At the left boundary, it's easy because we have this large N factorization assumption, which says that f of t is equal to the disconnected answer plus something that's formally 1 over n squared. And at the left boundary of the strip, there's no competing large parameter. Time is small. So this term here can be bounded by an epsilon that's like a constant divided by n squared. The top and bottom boundaries are harder because the time can be large, and in fact, factorization fails there. But we can bound the function using Cauchy-Schwarz at the top and bottom of the strip in terms of a different function, a different 4-point function, for which factorization should not fail. So let me explain that. This thing on the left-hand side has this path integral representation, where factorization here will not hold at large t because the w operators represented by the blue dots are very far from each other along the contour. On the other hand, this expression here, this is the path integral representation of this 4-point function. The w operators are close to each other, the v operators are close to each other. The only thing that's becoming large as t becomes large is the separation of the 2 pairs. So in fact, as t becomes large, this factorization should only get better for this quantity. Okay. So we expect that the right-hand side of this equation should be equal to this disconnected answer plus or minus something which could be bounded by a constant divided by n squared, uniformly in time. Technically, this is an assumption. We haven't proven this statement, but I think it's a very reasonable assumption. And there are some interesting special cases where it can actually be proven. Like for the application that Joao was talking about in the last talk, you can actually prove this factorization statement. Okay, but now we're done because we've bounded f on the left boundary and the top and bottom boundaries. So we have this inequality that the derivative must satisfy. And just to be completely explicit, let's imagine plugging in a ansatz for f of t is f of fd minus 1 over n squared times this growing exponential e to the lambda t. Then as soon as t is more than a couple times beta, you get the inequality that this lambda, the Leaponov exponent, has to be less than or equal to 2 pi over beta. Okay, so I'm done. Let me just summarize briefly. So I discussed how we can diagnose chaos in quantum systems by studying these out-of-time order 4-point functions. We saw how to calculate these in ADS-CFT. There's a really interesting connection between high-energy scattering processes in the bulk, in particular high-energy scattering near the horizon, and exponential growth of chaos in the boundary theory. Right, we used the initial exponential growth to define a Leaponov exponent lambda, and then we argued for a universal bound on this Leaponov exponent. Well, okay, here I only argued for it in a restricted class of systems, but in the paper we argue in a more general context. And to be fancy here, I've put in k Boltzmann and h bar. The bound would be 2 pi k Boltzmann t divided by h bar. And this, again, is saturated by systems that are dual to gravity. Okay, thank you.
found in the example you mentioned was the analyticity of f in the strip. You used that strongly to derive it. What was the physics of analyticity? Can you remind me again?
Yeah. So, well, so one thing you can do, good. I think it's easiest to explain from this picture here. The reason that it's analytic is that in this region here, the operators are all separated by some positive distance in the Euclidean direction. So the function is analytic for the same reason that, for example, Euclidean correlation functions are analytic in quantum field theory. If they're separated by non-zero distance in the Euclidean direction. So here we have a configuration of points where they have non-zero separation in the Euclidean direction. Sorry? Yes, yeah. So you can show that this thing is bounded by it's finite everywhere in the strip. Right. And so, but the edges of the strip here will be the points where the Euclidean separation between these operators goes to 0.
Any more questions or comments?
Yeah. So you showed that the Leaponov exponent is suppressed by large n corrections if you make an expansion around n equal to infinity. I was just wondering that if you just work with a finite n theory, in which n is not necessarily large, is it possible that we are dealing with really perhaps a near integrable system which behaves this way as n goes to infinity?
Are you thinking specifically about a holographic theory, or you just mean a general?
No, I mean, my question applies also to a holographic theory, yes.
I mean, certainly there are systems without large n that are chaotic, like chaotic spin chains, where you don't have many degrees of freedom per site at all. For that case, you wouldn't define this initial exponential growth by saying it's 1 over n squared terms the rising exponential.
Yes.
You have to have another small parameter, like, for example, the separation between the operators v and w. That would be a small parameter, and then you would have a growing function multiplying that.
Okay, thanks.
Okay, let's thank Douglas again for a very